Hi everyone, welcome to Black Hat. My name is Max Bazaliy, and today I'm going to talk about iOS dual booting. So I'm leading security research at NVIDIA Autonomous Vehicles Group, and most of my time I'm having fun with NVIDIA Driver stack. But previously I was working as a security researcher at Lookout and the Blue Box, focused on mobile security. So I was made various jailbreaks for iOS, watchOS, tvOS, as well as was after of Pegasus exploit white paper. A quick disclaimer, I don't speak for my employer, so this research is not related to my work at NVIDIA. It was just a fun personal project for me. So all the opinions, code snippets, and ideas, they're all mine. Dual boot, like what is a dual boot? Why do we need it? It's pretty much a process of having multiple operating systems on one device. And both operating systems, they can share the same hardware resources. But we have some freedom on which iOS version we want to boot. Unfortunately, Apple did not make our life any easier. So there's no low-level boot manager for iOS that we can easily switch between the versions. So we need to figure it out by ourselves. Why do we need dual boot? First of all, like quick experiments with the different operating system levels. For example, having iOS 11.4 and 11.1 on the same device and easily switch between them. Or, for example, for system recovery. If you're working on some persistent exploit for iOS and you're really scared that you can boot loop your device, you can boot in a second system and repair the corrupted file. Or, for example, even boot the second OS in a pre-jailbroken state, like load the kernel with disabled KLR, with disabled KTRR, with disabled all the mitigations, which make it perfect for different POC tests. If you want just to focus on sharpen your exploit and you have some unknown mitigation, you can disable just a few of them. So that dual boot really works for. How does it work? So the bad news, we need to create a new set of boot chain components, pretty much the bootloader, the kernel, the modified file system, sometimes the device tree. The good news is that we can bootstrap our second system from a RAM itself or from NAND. For this purpose, kernel or another bootloader can be used. And of course, we need kernel or bootloader level code execution. Like a few words about Apple Secure Boot. So the Secure Boot is our arch enemy on a way to dual boot. And there's a lot of papers how the Apple Secure Boot work. I just want to make a quick overview. So everything starts with Apple root CI public key in a boot ROM. And pretty much each component gets verified before the execution. So for example, boot ROM verified and load IBoot stage 1. Which verify and load IBoot stage 2, which verify and load the rest of the system, like kernel cache, device tree, and rootfs. In some of the operations during boot, SAP get involved, mostly to provide secure random number generator. So here's how the Apple boot process looks like. So Apple support local and remote boot. And the main difference, are we booting from NAND or are we booting from DFU mode? So boot ROM checking, are we currently in DFU mode? If we are, it expects IBSS image to be uploaded over the USB, verified signature. If everything is OK, IBSS gonna load the IBAC, and IBAC gonna boot the rest of the system in remote mode. In the case of local boot, boot ROM will try to boot ILLB from NAND. If everything is great, ILLB will boot IBoot and continue to boot the rest of the system. There is a few changes since iPhone 7. So on iPhone 7, Apple increased the amount of static RAM in a boot ROM. So now it can load like much larger bootloaders, which means that now boot ROM can boot the ILLB, and ILLB, for example, can boot the rest of the system by passing the IBoot. The same for DFU mode. All right, so boot ROM. and bootrom implements the IMG4 image verification. So IMG4 is pretty much a container that contains a payload, that contains decryption keys for a payload, and a payload manifest. The most interesting part is the manifest. The manifest is pretty much the set of the different properties that get verified during a boot. So each property from manifest, compare it with a property from a device, and if all of them match, then bootrom will pass the execution. So for example, one of the properties is payload hash, to make sure that payload is not modified, nonce, to make sure that we run this specific iOS version on this specific device. That's pretty much the way how Apple prevents a downgrade. ESC-ID, or like a board ID, to make sure that we run the firmware only for this device, and so on. So if everything is great, all the checks are passed, bootrom will decrypt the payload and execute it. A few more things may happen. First is, if the payload image and payload manifest contain the specific properties, the bootrom can do the software override for fuses, for like production and security fuse, and pretty much switch device from release mode to development mode. In other words, it can re-enable the JTAG. Of course, it's really secured by Apple signature. Another thing is ROM manifest hash is the thing for iPhone 7 and later. And the basic idea is that bootrom calculate hash of the payload manifest and save it in one of the hardware register and log this hardware register. And during the next component verification, this hash will be compared with the payload manifest hash of the next components. It's to prevent the mix and match. So, okay, the bootrom verified all the payload. It load and execute the payload, which is stage 1 low-level bootloaders, IBSS or ILLB. The only difference between them is it's just for remote and local boot. In the case of IBSS, it just await for iBack image to be uploaded over the USB. If everything is great, verifies and boot it. In the case of ILLB, it just boot iBoot image from NAND. If something is wrong, switch back to DFU mode. Both bootloaders, they perform IMG4 checks, the same as bootrom, the same mix and match prevention checks. They're stored in encrypted IMG4 container, so Apple still not ship them decrypted. But luckily, there are some keys available on public that really help us to check how the bootloaders really work. And since iPhone 10, Apple made some refactoring work, so now all the bootloaders is pretty much one binary that can be running in a different code path, like in local or remote boot. So stage 2, iBack or iBoot. Again, for local and remote boot, both can load the kernel cache, both can load the device tree, the RAM disks, and since iOS 12, now they can load the trust cache. They perform IMG4 checks, the same mix and match prevention checks, still encrypted. And Apple made some refactoring by merging it to one big binary. Device tree, that's an image which basically represents the hardware mappings. That's a way for a kernel to communicate with low-level hardware. So during a boot, iBoot or iBack, they set up various entries of the device tree. And later on, kernel will read these entries, map the addresses if needed, set up the properties. Since iOS 10, it's not encrypted anymore. It's still signed, it's still wrapped in IMG4 container. And there are a few container types for remote and local boot. The next component of a boot chain is a kernel cache. So the kernel cache is pretty much the XNU kernel and all the kernel extensions, which are statically linked to a kernel. It's parse the device tree, map the addresses, set some of the properties. And in the case of iOS 12, now the iBoot map the static trust cache in the memory, and the kernel now read it from one of the device tree entries. Next is going to load the SEP firmware, like SEP-OS, Wi-Fi, baseband. It's still signed in IMG4 container, not encrypted since iOS 10. And there are a few container types for remote and local boot. The next one is RAM disk. So the RAM disk is like a set of like minimum OS image. So it's like minimum set of frameworks and command line tools that use it for restore and update purposes. And that's why we have two types of RAM disk. The only difference is that restore RAM disk, it wipe everything from an end and then flash the firmware. And the update RAM disk, it's not wiping an end, it's just updating the different deltas during the update process. Since iOS 12, Apple moved static trust cache to a separate file per RAM disk. So now each RAM disk gets its own static trust cache that need to be loaded by iBoot. Yeah, it's not encrypted anymore since iOS 10, but still sign it. And finally, the trust cache, the new thing in iOS 12. So it's a file that contains code directory hashes for binaries that are stored on the RAM disks or the root FS. So each RAM disk, when it's get loaded, it requires the trust cache image to be uploaded first. And there are two container types, again, for local and remote boot. During the restore time, iOS will look for /boot/iBoot firmware in a restore partition to read the trust cache for root FS. In a case of normal boot, it just look for file system firmware-fud static trust cache image. So again, instead of, like later on, it was kernel. The part of the kernel was a static trust cache. It was one of the data in a const segment. Now Apple move it into a separate image for security purposes. So iBoot map it, and it's a new read chosen memory map trust cache entry, and using one of the pmap functions basically to map into memory. So it's just a theory how the modern secure boot works on modern Apple devices. And now I want to move more to like reverse engineering the Apple firmware. So it will be maybe a little bit more fun. Okay, so iBoot and iBack. So that's level 2 low-level bootloaders. They both support the different set of commands. And these commands they're widely used during the restore and update process. And unfortunately, on recent iBoots, there is no visible menu, but the command handler still exists. So if we know the command name, we can send the command over the USB, and bootloader should react. The trick is that bootloader should be in recovery mode, and we need to use iRecovery-C to send the command. So what are the commands? Basically, all we need to do is just to grab a decryption key, decrypt one of the bootloaders, and use any disassembler, and look for bootx string. So as we see, each command, it's wrapped into its own struct, and the struct is command name, pointer to command handler, and some of the command description. Apple usually wipe out the command description, but even this information is still enough. So we can map each command name to each command handler. And here is an incomplete list of commands that are supported in the recent bootloaders. For example, like RAM disk. RAM disk is a command that allows us to create the RAM disk image just from memory. So we can upload RAM disk over the USB, send the RAM disk command to bootloader, and it will try to create a RAM disk object. The same for device tree. We can upload device tree over the USB and create it just from RAM firmware. That's basically the way how Apple uploads the trust cache and verify the trust cache by uploading the image and send the firmware command. And I believe they, in a future version, they're going to move more and more firmware to be uploaded by iBoot instead of the kernel, I think for security reasons. Anyway, for now, firmware just loads the trust cache. The next is bootx. The bootx, it's a nice command. It allows us to boot the whole kernel cache just from a memory. So we can upload RAM disk, device tree, trust cache, then bootx, and here we go, the system will load. fsboot, that's the opposite of bootx. It say, hey, bootloader, please boot a system from file system, from NAND. the same kernel cache, device tree, and this rush cache. And the last one is go. So that's an interesting command. Basically, that's the way how Apple upload different diagnostic images to iBoot. So we can upload different images over the USB, then send the go command. And if the image tag is correct, it will be executed by a bootloader. OK, so let's switch back to dual boot. So the plan is we can bootstrap our fixed bootloader from a kernel. That's the one way. For this purpose, kernel code execution required as well as tool called the Kloader. Or we can execute our fixed bootloader from another bootloader. In this case, bootloader code execution is required. If we choose the dual boot from a kernel, most of the dual boot that use the kernel, they all base it on a tool called the Kloader. And the main idea is, as soon as we jailbreak our device, we can get kernel read-write exec primitives. We can take a bootloader that we modified. We can write it back to a specific address into physical memory and change lower set vector in a kernel to be bootstrap our new bootloader. So again, the idea is the bootloader will load the kernel. We write to a kernel memory the new bootloader and jump back to bootloader. So it's kind of like a big hack. But that works. And the Kloader is in a base of CoolBooter tool by Jonathan Seals. And the CoolBooter will do most of the things for you automatically. It will download the firmware, it will decrypt it, it will set up the partitions, and so on. Unfortunately, it's only work for 32-bit devices and OS versions. So the latest device with support is like iPhone 5C. There was a few attempts to port Kloader for 64-bit devices, and the most successful one was Kloader 64 by Axiomics. It supports some of the 64-bit devices, but there's still a problem that it limited up to iOS 0.8.4.1. I will show you why. So since iOS 9, Apple introduced Kernel Patch Protector, or the KPP, and more advanced version of it in A10 devices, KTRR, which lock the kernel memory and prevent any write attempts to a kernel memory, which means we cannot really map our new bootloader to physical memory. It's chicken and egg problem. There's few ways to bypass it. The last successful one was by Luca Tedesca in Yalu 10 jailbreak. But still, even if we can disable KTRR, there's still some trust zone map issues. There is a trust zone memory overlap. So in other words, the dual boot from kernel not really working on the newer system. One more thing that I didn't mention, the GID key. The GID key is the key that uses it to decrypt the firmware. And in a time when the kernel is loaded, it's already locked. So even if we jump back to bootloader, the key is already locked, and we cannot decrypt the new firmware. Which means kernel way of dual booting, it works, but it gets its own limitation. So why not try to dual boot from another bootloader itself? So we're going to bootstrap our fixed bootloader from another bootloader, which is going to load the fixed kernel cache, fixed device tree, RAM disk, firmware, all the stuff that I mentioned. And finally, we boot the kernel cache. So we boot the system just from RAM, and we get the SSH access. I will show you how we can write the rest of root file system to an end and boot a second system. So that's the plan. But on the way to dual boot, there are a lot of patches required. As I say, we need to create our own set of bootloader components. And here is a set of patches that I found useful during my research of dual boot. So for example, for IBoot and IBoot, it's really required to disable code signature check like IMG4. I want to show you how. It's nice to have to disable KSLR if you want to boot the second system with disabled mitigations. Or for example, to inject these custom boot arguments. because the release iBoots, they do not support any boot arguments from NVRAM. For XNU, for a kernel itself, it's required to disable code sign. It's nice to disable KTRR, like kernel text read only region. I will show it a little bit later. It's nice to export task repeat 0, or even remap the whole kernel as readable, writable, executable. As for RAM disk, all we need to do is just to add the SSH client and some minimal set of command line tools that we need to play with. Device tree, again, it's not really required patch, but it's nice to have if we want to boot the second file system with the second iOS system with UI. We need to disable the feasible storage. And finally, trust cache is one of the alternative ways of disabling the code sign. We can just add a new entries to a trust cache. So this is how it looks like. For iBack and iBoot, there is a function image for validate property callback, which compare each of the properties from a boot manifest and compare with the same properties on the device itself. And if all the properties are good, it's going to continue a boot. And it gets reference to from image for load. It's easy way to find it. Just look for one of the properties, for example, BNCN, and there will be only one reference to image for validate property callback. So all we need to do is just to scroll down to the end of the function, and we will see a reference to stack check fail. And before that, it will going to calculate the return value. Just make sure that we always return 0 into x0, which means like all the checks will be successful. Boot arguments. So the problem is that release iBoot, they do not support any custom boot arguments to be passed to a bootloader, which means even if we can somehow write boot arguments to NVRAM, the release iBoot will just ignore them and continue to use the hard-coded one. So as we see here, there is like one of the restore boot arguments. What we can do, we can just change them, right? If we can patch the bootloader, why not? So what I did, I just changed the boot arguments to add debug to set the debugger capabilities into a system. I set the serial to enable serial output for a kernel boot, and RD equal MD0, which means, hey, system, please boot from the RAM disk itself. The next thing is KLR. Again, it's not really required for dual boot, but it's really nice that we can boot the system with not relocated kernel. It's easy to spot. Just look for kernel -% string reference, and we will find a code that asks SEP to provide like 8-byte seed. In our case, it's random get bytes. So after random get bytes, we'll see the calculation of KLR virtual slide and physical slide. In my case, it's x8 get a virtual slide and x19 get a physical slide. Unfortunately, there is like in a release kernel and release iBoot, there's no easy way to disable KLR, because Apple just strip out the code that respect KLR of boot argument. But what we can do, we can relocate it with a 0 offset. So in my case, I just put 0 in x8 and x18 and snap out the rest, which means that kernel will be relocated with 0 offset and stay in the same address. All right, go. So the go command, as I said, that's a way how iBoot can boot different diagnostic images. And there is a check. There is a check for payload type that get uploaded over the USB. So for example, if you look for SEBI string, you will find a char array with all the supported tags. In the case of iOS 12.1, is like 7 tags are supported. And what this function is going to do, it's going to like read the payload tag and compare with one that's supported. So that's easy to fix. Just make sure we pass 0 instead of pointer to array, and we pass 0 as a count of different supported tags, which mean no tag is supported, which mean like every tag is supported. The next thing, I think is the last one for IBoot is KTRR, or like kernel text read-only region. That is specific mitigation that Apple introduced in iPhone 7, and the idea is Apple get their own custom memory controller, and Apple set up the region which the kernel will map it on. And when the kernel is mapped and finish all the initialization process, this region will be locked. So which means there is no way to write to this region as the lock made on a hardware level. In addition to this, the MMU get configured that no code can be executed outside of the region. So that's pretty nice mitigation to prevent the jailbreaks. But again, if we control the bootloader, we can disable it. The good thing, Apple, for some reason, Apple still respect unsafe kernel text boot argument. I don't know why, because we can't set any new boot arguments as they are hard-coded. Anyway, it's just a nice way for us to find the code. So as we see, if unsafe kernel text boot argument is set, then we skip the security set KTRR region. Otherwise, the KTRR region begin and length will be set up. So what we can do, we can just jump it out, nop it out, or even inject unsafe kernel text. Again, I believe that this code is part of some debug. It's left for some debug purposes, because it's stripped out in release kernels, but for some reason not stripped in the iBoot. The same story for KPP. It's like previous version of kernel patch protector, the secure monitor. Just look for monitor to large string, and we'll find the code that just loaded. Nop it out, and we're good to go. As you can see, there's maybe a lot of fun to reverse engineer the Apple firmwares, especially with their obfuscated logs and no symbols. So what I'm going to do next, I'm going to switch to XNU. It will be less assembly code and more C code, as likely the source code is available. So for XNU patches, the first thing is task for PID. That's the way how all the jailbreaks export the kernel task port. And the kernel task port is the way for easily read, write, and even allocate memory in a kernel. Of course, there is an explicit check if we trying to request task port for kernel. If PID equals 0, return kernel failure. Just if we can patch a kernel, just patch it out. There is more additional mitigation starting from iOS 10.3. So now Apple add task conversion evaluation code, which means if I believe this code added to mitigate ion beer exploit chains. The idea is if you're trying to achieve the kernel task port, it's going to return null, or if we're trying to get the task port of any other process, and we are not running as a platform application, it's going to return kernel valid security as well. So make sure you patch it out as well. Next one, the code sign. There's a ton of ways to disable code sign if we can patch a kernel. And one of the ways is what I prefer is PEAC and has debugger. That's the function that basically enable globally enable debugger capabilities for a kernel and for all the kernel extensions. And it just refer to debug enabled variable. So we can patch debug enabled to 1, or always patch PEAC and has debugger to always return 1. So KTRR, even if we disable KTRR in iBoot, the release kernels, they still there's hard-coded code that's always set up the kernel text read-only region. So there are a few things that we need to patch. Just look for MCC. So MCC is one of the name of device tree entries that get parsed by a kernel. And the thing is, all this code is just parse the device tree entry and set up read-only region begin and read-only region end variables. So all we need to do, make sure this code is never get executed in a kernel. The second part for KTRR is read-only region lockdown. So this is where the kernel already set it up, get initialized, and this is where the region get locked. So in our case, it's lock MCC and lock MMO. This code is easy to spot for iPhone 7. Just look for 0x7EC magic, and you will find a bunch of MSRs that we need to patch out. So in other words, the region will be never locked out, and in other words, it will not enable it. One last thing with the KTRR. So there is a low reset vector base that's the code that gets executed when the device awake from a sleep mode. And this code is checking if read-only region begin and end is like more or equal to 0. If it's equal to 0, just it's skipping KTRR. If it's not, it just set up again the KTRR region, lower EL1, upper EL1, and finally lock EL1. So our need is just to knock it out or make sure that read-only region begin and end are always 0. Even if we disable KTRR, there is one more thing in 810 devices. So Apple called it static mappings. So the idea is to now that page tables itself, they are allocated into read-only region. So data const will be writable where the page tables will be allocated to. And when it's done, this region will be set up to be read-only, and on top of it, the KTRR region will be locked as well. So even if you disable KTRR region, you still need to deal with the static mappings. But if we can patch a kernel, we can disable it during rmvm prod init or rmvm prod finalize. In my case, I just remap all the region to be readable, writable, and executable. There are a few more things that we can patch. It's not really required, but it's a nice one. Like Mac mount to easily remount file system to be readable, writable, or amphi code directory is in a trust cache. So that's a way how one of the kernel extension check is the binary we are running, is it trusted or not? And if it's trusted, it will be automatically get platform application capabilities. So we can patch it to 1 that any binary will be platform application, for example. And set UID to easily escalate privileges from user mode. But as I say, it's not really required. All right, we going back to our boot chain. So we already made the patches for a bootloader. We made the patches for a kernel. Now it's time for the RAM disk patches. And the idea is we just take a restore RAM disk, unwrap it, grow its size a little, and find the restored external service. And the restored external service, that's the one that will be executed when the kernel will start execute the binaries and the LaunchD will execute it. In other words, that's the one that we need to replace. We need to replace with our service that will start USB device MOOCs and spawn the drop beer, so we can connect to a device over the SSH. And the tricky one here is that we need to sign our fake daemon with the same application IDs, because there's one of the mitigation from iOS 10. The LaunchD now get a hard-coded list of the IDs that can execute, and if our ID is not one of them, it will be prevent. As well as we need to provide the entitlements that get access to get access to USB device MOOC service. Finally, wrap everything back and sign as RAM disk container. So this is how our restored external daemon may look like. Part of this code is already open sourced, and the basic idea is that we need to start USB MOOC service by creating USB device descriptor with the type USB MOOCs only, and then set USB device controller, USB device description serial. The idea is that to calculate the UDID of the device and set it as a serial per USB device description. Finally, create USB device controller and set the debug level in one of the services at 7. I don't want to really focus on it because there is a source available and there is a link at the end of the presentation if you want to know really how it works. The idea is to set the USB and despawn the drop beer, the SSH station. Device 3, it's optional patch that it's required. So what we need to do is disable the feasible storage. And the feasible storage is a special place where the data protection keys are stored. And to prevent the collisions between the two systems, we need to disable the feasible storage. As we see here, that's part of Apple IPFS text, and we see if no feasible storage entry exists, the Apple key store will disable the feasible storage and switch back to fake keys. That's what we need to make sure it's not going to override the original keys. Yeah, so again, just add no feasible storage entry to device 3, and we're good to go. Firmware or the trust cache. It's optional, just I would say a nice way to disable the code sign. Apple changed a little bit the format of trust cache entries. Now they introduced trust cache entry, name it 1. The only difference is now get the hash type and some of the flags. So the idea is we just need to add the new cache entry, trust cache entry, and make sure we change the number of entries in a trust cache model. And we're good to go. So if we made all the patches to boot chain, how to combine it all together? So we bootstrap our modified IBoot from IBoot, for example, from another bootloader. We upload each of the components over the USB, device 3, kernel, trust cache, one of the RAM disks, set the commands to bootloader to create these corresponding images, and finally boot the whole system with a bootx. We will get the restore RAM disk booted with minimal OS version and SSH access. So we can use, for example, TCP relay to connect to a device over the USB. But as I say, some of the kernel extensions are not started yet. So we need to force them to start. But that's enough. That's enough that we can take the current data partition and separate it into two new partitions, one as a new system partition, and another as a new data partition. Then upload the rootfs over the USB, and I write it to an end. Finally, patch the iBoot or iBack to boot from the new partition. I know it sounds a little complicated. There's too many things, so I just wanted to show a demo how this stuff works. So in this case, I want to show the iOS 11.4.1. I'm going to run it from my Mac. And the device is already in a pre-jailbroken state, so one of the bootloaders, it awaits another bootloader to be uploaded. So what I'm going to do, I'm going to use the minicom and to connect to a device over the serial and start uploading one of my modified bootloaders. Again, I recovery -F, and if the bootloader is in recovery mode, we can send our own stuff. So in this case, I send iBoot with disabled KLR and with disabled KTRR. All right, you get booted. So here we get iOS 11.4.1 release iBoot. Let's check that we are really running in recovery mode. Okay. And now we can set our modified components back to a bootloader. So I upload the RAM disk and set iRecovery -C RAM disk to force bootloader to load modified RAM disk. And as we see here, it's already uploaded. The same for device 3. We send the device 3, force bootloader to load it. Okay. Now I recovered C device 3. And finally, kernel. So I send the kernel with disabled KLR and with disabled KTRR, kernel text read-only region, which is really enough to play with some of the exploits and forget about the mitigations. Finally, I boot the system using iRecover.c bootx. All right, the system gets booted. And as we see here, that's showing the running server. So it's running the Dropbeer server. And now we can connect to a device over the SSH, over the USB. We got a shell. And yep, that's iOS 11.4.1 on iPhone 7. Let's prove that kernel is not relocated. So I use one of the tools that's looking for a kernel in a memory, and we see the kernel address is not relocated, which means the KLR is disabled. Next, I want to show that task for pit 0 is really working by reading some part of the kernel memory, for example, header. And finally, try to write some, like, for example, 4 bytes into a kernel memory. Usually, if KLR is not disabled, it's going to panic a device. Okay. So we write the 4 bytes, and now let's try to read them back. So yeah, as we see, we can override the 4 bytes of the kernel, and there is no panic. For iOS 12, it's a little bit different story. Apple add more mitigation on iOS 12 and change the boot a little bit. But the idea is exactly the same. We upload our own bootloader, which is going to bootstrap our own kernel, our own device tree, our own RAM disk, and boot the rest of the system. So I connect to a device using a serial cable. Proof it that we really run it in a recovery mode. All right. Yeah, in this case, I just disabled KTRR, but not disabled the KSLR. So kernel will be still relocated because there is some random panics that I see on iOS 12.1. So I decided to leave it as it is. So we are in recovery mode. Now it's time to send our modified boot chain. Okay. So the first is device tree. It's pretty much the same as iOS 11. Device tree get loaded. Now we send RAM disk. It may take some time. It's usually like 300 megabytes. Come on. And we send iRecover.c RAM disk to force bootloader to execute it. And now we see a difference. Yeah, let's check that it get executed. OK, the RAM disk get loaded. So now we see a difference between a boot in iOS 11 and iOS 12. So now the trust cache, the static trust cache, is required to be uploaded by IBoot. So we use the same iRecover.chef to upload the static trust cache and to force bootloader to load it in a memory using iRecover.c firmware. OK, and finally, let's boot a kernel. Okay, iRecover.c bootx. And we got our system booted. So it's all similar to iOS 11.4. We got the Dropbeer running. Now we can SSH to our device. For example, like using TCP relay to bind local port to remote port. OK. OK, we got a shell. So it's iOS 12.1 on iPhone 7. So in this case, as I say, I did not disable the KLR, so the kernel still relocated in the memory. But kernel text read-only region is disabled. So we can easily modify the kernel memory, including the kernel text region. So I'll read the kernel header, the same as in the previous demo. And now I'll try to write the 8 bytes in a kernel header to prove that KTRR is disabled. OK. OK. So yeah. As we see, no panic, and we can read the same bytes back. So KTRR is disabled on 12.1. So this was a demo of the dual boot of having 2 multiple OSs on the same device using the bootloader. And of course, there are some issues. The main issues is there's some incompatibility on SEP-OS side. So SEP-OS is operating system that runs in a separate physical CPU. And we don't really have a control how we can update the SEP-OS, which means there's some incompatibility. For example, iOS 11 and iOS 12, they have a different protocol, how the SEP-OS communicate with the kernel, which we can't really dual boot 11 and 12. But we still can do 11 and 11 and 12 and 12. So the major versions still work. Again, we don't really control the SEP update process, as we need some code execution on the SEP-OS side. And even if we do, we need somehow to dump the SEP anti-replay token. There is some research made on it, but it's still not complete. But what we can do is to load the custom drivers or the custom kernel extensions on A10. As we see, with disabled kernel text read-only region, we can map our own memory, we can write our own drivers, and that's it. And one of the plans that I got to make some low-level boot manager for iOS, for example, as a wrapper for iBoot to easily switch between 2 operating systems. I think we still have some time. I want to get a quick overview what the iOS hacking will be. So the last year, Apple introduced A12 SoC, and it definitely raises some bar on the security. I'm pretty sure many of you hear about pointer identification codes that Apple introduced in the newer iOS and on newer devices. And we know that it exists in the kernel itself and in a user mode. But the bad news, it's not just there. Now it's in iBoot, it's in a kernel cache, it is in a user mode, it is in a SEP-OS, in SEP user mode level. Additionally, they add some software CFI in critical boot components, as well as add the new secure storage where the SEP anti-replay token now is stored. So that's interesting. They made some mitigation on static trust caches. So now the static trust cache, as I said, it gets loaded by iBoot itself. It's not a part of kernel anymore. The dynamic trust cache now moved to IMG4 container, so they drop completely IMG3 container types. They made some refactoring on the way how kernel perform the code signature check by introducing the core trust. And finally, even in a WebKit, there is some hardening, including usage of pointer identification codes. So yeah, that's A12 jailbreaking may be a tricky one now. Here's a list of references that I used during my research. I really highly recommend to read the Xero write-up about IBoot exploit for 5S, for 32-bit devices, which can be ported to 5S, and, for example, using the same steps that I do the dual boot. And here's a number of folks who helped me during my research. I just want to say thanks. Yeah, I think we still have time for questions. Thank you. No questions? Okay, even I will be around if you have a question. You can catch me somewhere in a coffee area or in a hall. So I think, yeah, we saved 10 minutes. I'm done.